Thank you. So, hello everyone. Thank you for coming. I'm gonna tell a story. If the genre is adventure with elements of bug reporting. So we try to do the shrinking of dynamic libraries in the system to save size. And we chose to use the linker plugin API to do that. It seemed convenient. Let's see how it went. By the way, if you want to click on the links in this presentation or just impatient to see the rest of the slides, you can get them from compilers.ispress.ru/materials/plug.pdf. During this talk, I mean. So the problem was this. We are given a software, an operating system distribution. It has shared libraries for whatever reason, and it's immutable once it's installed onto a device. So there are no packages or executables which could be added after it has been installed. So the fact that it has shared libraries makes the problem new, because if it didn't, then for static linking the problem has been solved before. I'll show it in a minute. And the immutability makes it solvable. Expand a bit on immutability. We assume a closed world setup. It means that we control the toolchain which builds everything on the system. And yeah, as I said, nothing is added afterwards. So there are no potential future users for the API. The interface, the needed interface is fixed, so we can work with it. So in static linking, the problem has been solved before, and what you need to do to make it work is first compile with a function sections, a data section switches. What this makes is it puts every data object and function into a separate section in the output file. By the way, we only dealing with ELF format. So yeah, instead of having just .text there, we have .text.foo for the function foo. And that's it. It's needed because linker only operates in terms of sections, relocations, and symbols. It doesn't know actually about functions. So the second step, you link with --gc sections, and this causes the linker to omit unreachable sections. It starts from the entry point of your executable and traverses the graph of sections, marks them as used, and the rest can be thrown away. So what about the dynamic models, dynamic libraries and executables? There is no reason why GC sections cannot be applied to those. It can, but it does not produce much. The effect is relatively small, because in case of dynamic libraries, the set of roots is much larger. Effectively, it's the whole interface of the library in case of dynamic library. And so starting from those, you can usually reach pretty much everything there is in the library, so nothing gets thrown away. And in our closed world setup, of course we can figure out which interfaces are actually used, and tell us in some form, provide this information to the linker. So then it will do a better job having this global knowledge, which is used, which is unused, and then it will start from the roots and throw away. it can do so automatically if we change the symbol's visibility attribute to hidden value, because hidden symbols do not comprise the API. There's no reason to keep them. About the global graph I've been referring to, we need to build it. Okay, so the basic concept is a dependency. So there's dependency in this listing from symbol main in a.out to puts in libc.so. It's quite simple, right? Just a function call, and I call them link time dependencies because the linker sees such dependencies at link time as relocations. There are harder cases, of course, such as runtime dependencies, say via DLSIM interface. The linker has no way of knowing. It could have been user input instead of malloc at that point. So no one knows what symbols, what dependency edge we should add, and it's in dashed line there. Malloc on a.out to malloc in libc.so. And there's actually an even worse case where interpreters, such as, say, Perl interpreter, might expose the DLSIM interface to the Perl programming language, and since GCC does not have Perl frontend, we won't see it at all. We won't be able to reason about such dependencies. And of course we don't. And also people could manipulate ELF data structures in C like DLSIM does, except it would be their own DLSIM. So in these cases we just punt completely, or rather we provide the user with a possibility to annotate, to add manually edges to our global graph if they know the dependencies. About the runtime dependencies via DLSIM, sometimes they are computable if it's a string literal or some such, and we wrote a paper. You can read it or just ask us if you're interested. But this talk is focused on link time dependencies for simplicity. So the high-level approach is to first record all the link time dependencies from each link, because the linker sees it. We can record it. Second, combine all those dependencies into one global graph, traverse it, and infer the information about which symbols are ultimately used. And then at step 3, we eliminate unused symbol during another whole system rebuild. So that's it. We implemented steps 1 and 3 as plugins to the linker and the wrappers. So yeah, this approach is kind of good in that it avoids patching the tool chain. So customers probably won't be happy if we told them, hey, you have to use our patched GCC, patched linkers to make this work, to shrink the libraries. So the plugin approach looked alluring. It's also good because it avoids duplicated work. We don't have to do the R archive machinery and packing by ourselves. The linker already knows how to do that. There is one subtle point though, that the linker API was created for the use with LTO plugins. Actually, both linkers, the traditional BFD linker and the new gold linker, have loops iterating over an arbitrary number of plugins. So in theory, you could do whatever you want with this interface, which it allows. But if there is an LTO plugin already present, then we are in a predicament. If an object file contains LTO IR bytecode, then if the LTO plugin sees it first, it looks at it and it says, "Yeah, I'm claiming this file. I know what to do with it." It tells the symbol table to the linker, and then it calls the compiler, compiles it, and adds the compiled object, new compiled object files to the link after, which will be processed after all the regular files were processed. But in this case, our plugin won't see this file at all, because linker plugins only see the original object files. They don't see the files linker plugins added to the link. In case our plugin sees it first, it won't know what to do because it doesn't speak LTO bytecode. So we had to disable LTO in order to be able to collect the information. I already mentioned the claim file handler. Probably people here know how LTO works, right? Show of hands. LTO? Okay, fine. So it's less than half. LTO works like this. Well, basically, I already said that there is a claim file handler, which linker calls. The plugin provides this handler, which linker calls, asking it, "Do we want to claim this file?" And if the plugin claims, it knows what to do with it. It tells a symbol table to the linker, and then does its magic. So the plugin, our plugin registers this a hook for the handler, and what it does, it simply walks the elf date structures to figure out what symbol it has, what relocation it has, and just records this information. There are intra-DSO dependencies and inter-DSO dependencies, which are given respectively by relocations resolved inside the module and unresolved relocations. So that's it for the first step. The second step is analyzing the global graph. First, we have to merge the graph and then traverse it. It's relatively straightforward. The graph is this. The set of nodes is sections and symbols of the object files, and the set of edges is relocations and definitions. If a symbol is defined in a section, there's an edge. The only non-trivial point here is EH frame sections. That stands for exception handling. For some reason, they're not normal sections in that there is no pointer to them from say regular sections of functions throwing exceptions or some such. So we won't reach it during this analysis. So there's a hack to explicitly traverse personality routines for exception handling. And now for the third step. First, People familiar with linker scripts probably know that you can hide symbols by supplying a linker script which would make them local. In this linker script, only two symbols are not hidden, the DL start and DLS3, and all the rest of them are hidden. In this case, it's muscle libc. So we build it, specifying the linker script, and it shrinks like quite significantly. In this scenario, only the dynamic loader is preserved. Everything else is thrown away. Why did I use muscle libc, not glibc for this example? Anyone?
Because glibc already uses the linker script.
Right.
Yeah.
So if there is already a linker script, you can supply a second linker script. And of course, you can modify on the fly the linker script, but it seemed tricky, and we didn't want to go this route. So what approaches did we actually use? Well, first, let's take a step back and think at what time can we throw something away. Basically, there's the compilation step and link time. At compile time, if we, well, first, this approach is constrained because compiler does not see everything. It does not see assembly files, for instance. So if it doesn't throw away something from an assembly file, we'll be in an inconsistent state. If something on which this assembly file depends has been thrown away, we'll end up with an undefined reference, not something that we want. And also, it can only throw away symbols which aren't needed in all of the links, because the object file will be used in all of them. And so yeah, if anyone requires it, then we have to keep it. And at link time, this step is required for consistency. Source language doesn't matter, and elimination happens on per dynamic module basis. So the first implementation we made was just this: enable GC sections with a wrapper to the linker. And set the hidden visibility via another linker plugin. This plugin works in about the same way as LTO plugin works. It claims the input file if it knows, if it sees the file contains a symbol it wants to make hidden, it claims it, and it rewrites ELF. There's a small amount of patching. You need to just adjust the visibility bits and adds it to the link, and the linker sees it for the second time. It grabs it and does the linking with the hidden visibility info, does GC sections, and unneeded symbols are thrown away. Looks good, doesn't it? However, we stumbled on a number of bugs with this approach. For instance, the BFD linker is black magic. The deal with the BFD linker is it uses BFD, which stands for binary file descriptor in this case, to hold to point to a BFD represents an input file. So each input file gets a binary file descriptor associated with it. But not only this, but linker also creates its own sections during its work. And what it does, it puts the created sections inside BFDs representing normal input files. So it's not a very good thing to do. And the bug was first discovered in 2016 and fixed for LTO. However, our approach, our plugin claims more files than LTO. And what happens is the linker finds first BFD which was not claimed. And in our case, since we claim CRT files, it happens to be a dynamic library. And it adds a dynamic section to a dynamic library, and then it finds the wrong dynamic section in the library and just crashes or whatever. So in the same thread where the problem with LTO plugin was fixed, Jehyung Lee proposed a patch to apparently amend the situation, but unfortunately it was never applied. And the funny workaround we have for this bug is provide a dummy.o for each link, which contains nothing basically. It just has to be a valid elf. So BFD finds it and gladly stacks whatever it wants inside the BFD representing this file. It's not a hard bug, but I thought it was funny. Here's add symbols is callback that linkers provide to the plugins. The plugin has to tell which symbols are in the file it sees. So the important piece here I want to draw your attention to is name and version is this LD plugin symbol structure. Version symbols are part of ELF standard for compatibility. And the thing is, the linker plugin has to provide this information to the linker. However, let's see where this symbol version information can come from. It comes from two sources, basically. First, it can come from a version script, and in this case, the linker knows what to do. It has always known. The other case is assembly files and .simver directive. And assembly files, assembly code comes from two sources, from assembly files themselves and from inline assembly in C files, say. So, in the normal operation of the linker, if it sees a file with simver which came from assembly, it also knows what to do. It's a valid elf, it has the symbol version where it has to be, and knows what to do. Same goes for inline assembly, because it ends up in the elf anyway. Now, in case of LTO plugin, if the simvered file comes from regular assembly, the LTO plugin just does not claim these files because they're assembly files. They don't have any Gimple IR, obviously. In the case of inline ASM, the LTO plugin has to deal with it because now it's in the bytecode. But it has no way of knowing what version in the struct to set, because the compiler doesn't really know this information. It doesn't really parse or look in this deeply at inline assembly, and so it breaks. As Martin showed yesterday at LTO BOF, there's PR 48200 in GCC Bugzilla exactly about this bug. What about our plugins? Our plugin. It sees ELF, right? So in theory, it knows the version it has to set. However, since the LTO plugin is really the only test case for testing of the plugin API. It does not work consistently across linkers, and I'm not sure. Yeah, it does work for Gold, and it does so differently for BFD linker. I'm not sure how broken that is. So there's a problem. Another bug is with common symbols. So it's also a known bug. There is a link to it. And the thing is, if we have, this symbol is common. X-ray syntax options is a common symbol. We supply the archive with this symbol twice on the command line. And the R archives do not have the information about the common status of the symbol. They don't distinguish between common and regular definition. So what the linker does, it shows the file to the plugin twice, and in the end, we kind of end up with a multiple definition of the other variable that's in the file, the xremax failures, something like that. So, yeah, and also there is this thing which is not a toolchain bug per se. It's only an issue for invalid programs, which rely on the constructor order being the default, which is not the case when plugins are at play, because they can change the order of input files. Basically, probably it will be the reverse. But some programs depend on it, and we don't want to break it, because we want our tool to be as transparent as possible, so the user could just run it and have basically the same program, the same operating system they had before, with unneeded paths thrown away, and the runtime behavior same as before. All this took us to a different approach. So if we observe the ELF spec carefully enough, we'll see that any reference to a symbol contributes to its visibility. Namely, the most constraining visibility of all definitions and references of a symbol has to be propagated to the final symbol. So as we noticed it, we thought, aha, we can downgrade the visibility of symbols by supplying more references to them. Those references would have hidden visibility attributes set on them, and everything should be fine. This approach does not suffer from most, if not all, problems the first approach suffers from. So it also looked good. However, there are bugs. For instance, this one. We still rely on GC sections to do the thrown away part. We just set the visibility to the right values. And in Gold's implementation of GC sections, it does not basically respect the clause from the previous slide from the ELF standard. So if it sees a file, a symbol with a visibility attribute, and sees it again with lower visibility, it does not update. It has already set the state, and the GC sections won't respect that. So for us, it's broken. Of if the file with references is put first on the command line. However, it shall not be first, because in this case, the unpacking extraction from our archives will be different. We'll extract more than we extracted before. It's different link time behavior, and of course, not good for us. This basically brought us, well, that approach worked well enough, modulo this bug. But there is the third approach we took, and the idea was to not to rely on the GT sections machinery at all, and also not to rely on the linker plugin interface. Although we do rely on it for section reordering in this case. The idea is as follows. We can, if we look at ELF from the point of view of segments and sections, okay, we can throw away the tail of the segment. If we place all the unused symbols into the tail of the segment, after link, we can post-process it by chopping off the right amount and therefore get rid of the unused symbols and have the desired shrinking. Yeah, here's the illustration. Never mind the thinker there. It shouldn't say program header, it's self header. Otherwise, it's correct. The first thing to do, and we rely on the plugins for that, is to make the, no, we don't rely actually on the plugins, it's a patch to the gold linker. Unfortunately, it places .fini after all the text sections, so we had to tweak it a bit, just a couple of lines, moving enum values up several items. Yeah, so the text should go at the end of the segment, and then we can use the gold's plugin API to move the used sections to the left and unused to the right. And then we chop it off. Only we have to preserve the alignment constraints, so we can only throw 4K chunks. So if it's, yeah, there's a gray little piece there which is unused but cannot be eliminated due to this constraint. So the shrink happens, there you go. We have this shrunken binary now. Yeah, this the thing I have not touched before is reproducibility, which kind of plagued us when we implemented the first two approaches, because when you throw away something, you change what configure tests see when configuration of packages happen. And so, yeah, the build takes them different path, and everything changes. With this approach, we don't suffer from this because at step 3, the configure tests will probe the same unmodified binaries, and we'll draw same conclusions from them. There's also the potential to eliminate a little bit more because the configure test, the mains of configure tests, we don't really care for them. So they should not be roots of the reachability analysis. So it gives, yeah, some additional gain. Yeah, of course, obviously it doesn't suffer from the linker bugs, well, as much as possible it is. But it requires this update section order plugin interface, which is only available in gold. And a small patch for gold, which I already mentioned. And yeah, the alignment constraint, you have 4K missed optimization per segment, and it means probably 2 per a binary. And the remaining one is actually a big one because those sections, dynamic strings and dynamic symbol table, are quite big, especially if you have C++ programs. The symbol names tend to be quite long, and they take up space. So we'd rather eliminate that, but it's not that easy because usually they go into the same code segment, and we cannot do this trick with chopping off the tail the second time. We have to choose what goes at the tail, right? We cannot have unused text and unused dinster at the end of the segment, so we have to choose. Or we, of course, could, in theory, have another segment for such things, but it's also kind of wasteful in that, well, first, load time performance suffers, and you have the 4K problem again, though I'm not sure about that. So anyway, it's kind of hard, and we did not implement it. So the third approach is a proof of concept. It works for the code segment, and of course it brings smaller reductions, but there are fewer problems with correctness. Yeah, I think that's it. Thank you very much. If you have questions.
So, what are the results then?
Sorry?
What are the results then? So, how much,
the results.
how large was the shrinking?
Yeah. I mentioned the result in the abstract. Just they didn't make it to the slide. We tested on a Tizen distribution, and it gave us 10% reduction. Well, it depends very much on what you shrink, because if there are more programs in the system, they use more symbols, obviously, and the fewer there are, the bigger the reduction is.
Okay. Okay, well, that's already quite good. Then, well, why your third take to the problem is very inventive. It's a nice hack, I think. One problem would be with PC relative references from the data section into the from the data segment into the text segment, because the relative offset between both changes due to the chopping off of the text segment, so that would break if the offset is encoded, not.
Yeah, I see what you mean.
Relative offset is encoded,
actually,
which doesn't happen in
yeah, it's not a problem because we don't touch the virtual addresses linker already assigned. Due to we can chop the 4K chunks and preserve the virtual addresses.
Yeah.
Completely.
Right,
So
right.
it only changes the file on disk.
The file layout, yeah, it might actually. I'm not sure how the dynamic linker deals with that situation. It might just work, or it might work only in practice, but it certainly works, and it's very inventive. But I think you should actually fix the bugs in the plugin API so that your first approach actually works, because that's.
Well, it's tricky. It's a long-standing bug. If you mean the Simver bug.
It's the Simver bug, then the problem that re-injected object files are not seen by plugins.
Oh, I think it might be by design. I don't know.
That would be a bad design.
Have a knob in the plugin where you can say whether you will take away the object file and insert something else, or if you want to just process something and tweak it and keep it perhaps slightly modified, but
I think honestly, talking about a design of the plugin interface, it would be calling it too much. I think it was hacked together so it works with LTO plugins. So it's possible to extend it and make it work more usefully in your cases, I think, and that should be what should have been done basically.
So if there's interest for supporting such use cases,
and I think it doesn't make sense, for instance, that plugins don't see object files that were injected by plugins.
Because that basically means you can have just one reasonable plugin for the same objects.
Yeah.
So,
And that's a bad design, right? So
it works with GCC LTO and LVM LTO if both are using disjoint sets of objects, and that's probably the usual case, but otherwise you can't just have multiple plugins for the same.
Why have a plugin interface if it's not extensible, or if it's not useful for plugins,
It says I'm using the LTO plugin interface, not linker plugin, because it kind of only works for LTO currently.
For the wasted 4K you had in the slides, just one small comment from the time when I was hacking on Prelink is that a lot of the ELF sections are movable. They don't have a fixed virtual address or fixed address. Like if you have the relocation section or the dynamic symbol or a bunch of other sections, you from the ELF specification know this one is only referred from DINSIM, or this one is referred from here or something. And so you can easily move them any way you want, shrink them any way you want.
Yeah, that helps.
In Prelink, I had the opposite problem because I had to grow some of them instead of shrink. And in that case, sometimes I created a new PT load segment. There was no other way to move stuff around.
Does everything work correctly with multiple loadable segments?
Well, I
code
think the recent default with the linkers is that that 4 PT loads instead of 2 are generated or something. I would hope at least. We do at least just 3 and not 4, but nobody bothers.
Okay, thank you. Any other questions? Yes.
I have a question for the first pass. When you have to rebuild everything just to get the list of references or graph of references, is this approach noticeably more effective than just grabbing all the references in already built ELF files? You just grab all of the defined references. This set will be slightly bigger, but I expect it won't be much bigger. Do you have any statistics on this? I mean, just grabbing all the different references is much easier than rebuilding the whole distro.
Yeah, we also need to get the inter DSO dependencies, so we can walk.
My bet is you don't need them. You just grab all the references. You don't care what library provides them, actually, because, by the way, the specification allows other library to provide these symbols.
Oh yeah, sure, but
my question is whether your approach is more efficient. Have you any statistics?
No, but I don't see how you're. I'm not sure I understood you.
1% difference.
Sorry?
Or what if it's just a bit, whether it's really noticeably more productive? I mean.
Yeah, we don't have any statistics, okay. But I don't see how that would work. Yeah, probably you'll throw away much less, I think. Because the point is you walk the whole system graph to see what's unused, right? And often it's the implementation of interfaces which is not visible from outside the module.
Yeah. My bet is the difference won't be that big.
Can you state your approach again?
My approach is just to dump all undefined references in the whole distro and use this as a reference, and not to rebuild everything just to get a more precise graph of dependencies. I suppose the difference won't.
How do you drop anything without recompiling?
Yeah, just dump everything, not drop. I mean, the first pass when you have to find out what symbols are needed, you just dump all undefined references and all elf symbols. You don't have to rebuild anything at this stage. So my question was whether the result will be much worse or not.
Wait, no. How do you deal with the following situation? You have a library, you are now in the process of building a library, right? Which provides two functions, foo and bar. Now it so happens that in your whole distribution, the function bar won't be needed. But you won't find out at the time of building the library, because only when you build all the applications using that library, you will see that, oh, in fact, bar is not needed. But this is what they want to eliminate.
Yeah, that's clear, but the distribution has already been built somehow. It's already there. They want to optimize it. For this reason, they have to rebuild it once to get all references, and then to build it again and do something funny. What's the whole presentation?
What you mean? Okay, so
you
have the distribution, and then you inspect all binaries and only look at the undefined symbols, and only those that are actually referenced would be the necessary ones.
But then you have GLSIM.
Yeah, but they don't.
Yeah, this is a problem that's not dealt in this situation. So I don't have a solution for the.
I think it would work as well.
And also, it's not this is.
For GLSIM, the thing to look up the argument if it's a constant string is cute.
Yeah.
If it's not, then basically you need to look up all the shared libraries that could be DL opened.
That's all of them.
All of them anyways. Or you can of course look also for DL open constant string arguments. And if it's not constant, then just give up for everything.
Yeah. I'm curious, how many symbols have you found through this DLSIM argument lookup?
Oh, we found some. I have a mic thinking. We found some. I'm not sure exact numbers, but it's, I don't know, dozens probably, something like that.
Is it that much? Dozens? It's probably through Perl and other binding interfaces. Where the most of these symbols.
No, I don't actually remember where they come from, but in Perl you have. There's another problem, that you have an interpreter which exposes DLSIM, and then all bets are off. They are not constant strings flowing to that. They are whatever the Perl programmers wrote flows into that DLSIM, and we can only automatically discover constant strings flowing through arbitrary wrappers into DLSIM eventually, something like that. And for the rest, manual annotations done by the user.
There is probably one more problematic situation, I'm not sure. My experience shows that some library interfaces are used just in their test suites. So the result distribution doesn't use some symbols, but they're used just to build the library. And if you use the approach that edits the library during build, then the test suite will fail.
Well,
like, for example, I think a GMP library is one of these examples. The suite is much more demanding than.
But did you define that problem away, right?
Yeah,
he had in this problem statement
in the first
specific requirements, which was one distribution which does something which is probably not running test suites. So
in the first round,
you don't run test suites. How do you know that it works or not?
You QA it.
As usual, you test it.
I mean, that's
Yeah, obviously, if you need something, it has to be present at the first run. The first rebuild, you discover what you need there.
These symbols are not used just if they're used just in this suite, and you can actually drop them from the
Well,
result definitions.
then it's the kind of the DLC problem. If the test suite is built, then fine, they will be preserved. If it's not, they won't be.
But
You have to, it's a closed world setup. You build everything. That's the point. So you must build the test suite and you'll be fine. You build it both, the first step and the third.
But then you would like to drop these symbols because they are not used actually for the distro.
Yes, they are, because they are in your closed world.
Yeah.
Either they are in it or not. And you can.
Yeah.
They are both. They are and they aren't at the same time. So.
No, but in the closed world there is nothing, no difference between test cases or test suites and other more useful applications. It's just the executables.
Yeah.
Either they are there or they are not there. And if they are not there, then you can't run them, obviously. But then the symbols are missing, of course. You can't, after the fact, inject any other executables into the closed world and expect them to be runnable.
But you can have some executables in the closed world and then take them out for production.
Yeah, but then the closed world potentially contains too many symbols that are not actually needed.
Yeah.
That's
Which is
tough luck.
fine. Yeah. So, I guess that's it. Thank you.